Good afternoon, everybody. My name is Sarah Hunack, Chair of the Webinar Committee, and I'm really pleased to welcome you to another SRP lunchtime webinar in association with AURPO. Today's topic is Varskin, an introduction to the SkinDose module. So before we start, I'll just whiz through the ground rules really quickly. It will be recorded, this webinar, and we'll pop it onto our YouTube channel after it's finished. Questions can be asked throughout the presentation, and at the end, they'll be asked to the speakers. The most liked will be answered. So if you do spot a question up there that you'd like to hear the answer to, please like it, and then it'll get put to the top of our list. Any that we don't manage to answer today, we'll send to the speakers, and they will answer them for us, and we'll pop them up on the website for you. You can register your attendance using the code on the screen. Just email to Tegan, and she'll send you the CDP points. And as always, please, can you send us your feedback? We want to know how you think it went, what we can do better, and maybe suggestions for any topics that you'd like to see in the future. We've got an issue out of our radiation protection today. Issue 5 is available. You can click through to the website and have a look at that if you've not already seen it. It's our 60th anniversary edition. And then, as always, I'd like to plug membership. If you're not already a member, then please join us. Here are all the brilliant benefits that you could be getting. There's information on how to join on our website. And then finally, just before we start, some really exciting news. The 7th European ERPA Congress is coming to Liverpool in June of 2026. It only happens every 4 years, and this is the first time that it's come to the UK, so we're all really, really excited about that. And we're going to join it up with our annual conference in 2026. So put the dates into your diary and please spread the word. That's all from me. I'll hand over now to past SRP President and immediate past President of AURPO, Professor Pete Cole.
Thanks, Sarah. Hello, everyone, and welcome to another lunchtime webinar. I think the topic of today's webinar is extremely important in this time of robustifying, if that's the right word, our risk assessments and pressure from regulators on classification of workers. So I think it's incredibly important. It's my pleasure to introduce today's speakers, my colleagues and friends, Gwen Mott and Ralph Whitcher. Gwen, originally a geologist, her radiation career started as a radioactive substances regulator at the Environment Agency. Subsequently, she became a radiation protection officer in the higher education sector. She has over 10 years experience in universities and recently recertificated as a radioactive waste advisor. In 2015, Gwen joined her first SRP committee and is currently chairing the Research and Teaching Committee. She organises the regional AURPO London and South East meetings. Before entering into the world of radiation, she had a varied career, including contaminated land officer, translator of film scripts, publishing assistant, site geologist, and landscape gardener. Ralph Whitcher is from CLEEPS. Ralph is a science advisor and RPA for CLEEPS, the school science service, and a lead RPA for CLEEPS as an RPA body. As an AURPO member, Ralph is a member of the Executive Council Committee and is currently acting chair of AURPO's Higher Education, Research and Teaching Culture Group. Ralph is a member of SRP's Research and Teaching Committee, chairing it from 2009 to 2016. He is also chair of the Association for Science Education's Health and Safety Group, a technical committee that supports safe and exciting practical science by advising on how to do practical work safely. So without any further ado from me, I will hand over to Gwen and Ralph, and I think it's Gwen first.
Yes, thank you for the introduction. While Ralph is bringing up our slides, I just want to say, so the talk is a joint effort today between me, Gwen Mott, and Ralph Whitcher, who will be doing the first and last part, and you will hear me in the middle of the presentation. And topic is Varskin Plus version 1.2, an introduction to the SkinDose module. And I'll hand over to Ralph.
Good afternoon, everybody, and thank you for that kind introduction. So we're just going to go through Varskin. It comprises 4 modules. There's a skin dose, there's also the wound dose, the neutron dose, and eye dose. It's the skin dose we're focusing on today. And this comes from the experience that both Gwen and I have in using it. It's principally used for, what's designed for, measuring the dose, not dose rate, dose from skin contamination. It came back from way back from 1987. It was first developed, and it was designed for, at that point, for sort of hotspots on the skin. But it has been developed considerably since then, and it's got far more features. We'll look at some of those features today. And I think the key thing here I want to emphasize, it's far more than just something that works out the equivalent doses after receiving contamination on the skin. And I'll highlight some of the things here. Certainly it's useful for reviewing doses, and you can figure out dose rates in handling procedures. And also, which I found it very useful, for estimating doses from sealed sources nearby. Links to IR17, the Ionizing Radiation Regulations 2017, plenty. I've listed 5 there, I'm not going to go through them all. It's not just about, the last one I've listed there, assessing doses from accidents. It has far more uses, including things like deciding on designations of areas. And certainly what I've been using it for is in ACOP, Approved Code of Practice, paragraph 7071 on dose assessments and dose rates. What Varskin doesn't do, well, it's not going to predict the national lottery numbers next week, obviously, but things you might expect it to do, and it doesn't. So there's a limit on how far away the source is from the skin, and there's a limit of 20 centimeters. I think you can use it beyond that, but the results are unreliable. It doesn't assess doses from inhalation or ingestion, so internal doses. It's only external radiation on the skin. And it doesn't work the other way around. You can't take the dose and then figure out the activity of the contamination. And although it does, it's impressive actually, the number of geometries it can deal with. One of the ones it doesn't move directly is gripping a cylinder of material. But there are workarounds we'll discuss. Alternatives? Yeah, there are several. Delacroix is well known amongst us in the RP world. It is out of date now, frankly. It's 2002. It was reissued, new editions in 2013 and one recently, but they're in French. So unless your French is very good, it's not of much direct use. Curran has been mentioned. Curran only covers 6 radionuclides. It's in old units. Considering this was written in 1987, it's a bit annoying that it's still in the units of rads and curies when we changed over in SI units back in 1975. So it's of limited use. And there are formulae, for example, in Sember quoted here, which you can use if you know the activity per square centimeter. You can figure out the dose to the skin over time. There are problems using simple formulae, and I want to highlight it here. I won't go into too much detail, but you can see why simple formulae aren't going to work very well, because most formulae use either the end energy or the mean energy of the beta radiation. That tells you nothing about the shape of the spectra. And I've got here a graph on the left there that shows you the spectrum of sulfur-35 and carbon-14. See how different they are, but the mean beta energy is almost the same. And the second thing is to look at the chart on the right. Now this shows you if you like, the absorbed dose per beta going into a square centimeter of skin. And look how non-linear it is. And both the scales there are log scales. It is highly non-linear. So if you try and map the spectra onto the dose you get per energy, it is very difficult indeed. So looking at this particular case, the S35, the mean energy is about 1.5% lower than carbon-14. But like for like, S35 gives 10% higher dose than carbon-14. So using just the mean beta energy is not a good way of figuring out the dose you get from skin contamination. There's some calculations here to compare them. You can have a look. So I've taken P32, chlorine 3016, and chlorine 36 and C14. Semra and Curran significantly different to Varskin. Both underestimate at low beta energies. Curran is really high. It's getting on to 40-50% higher than what Varskin's given. So a little bit of caution using some of these other ones. The research on Varskin is pretty impressive. They've compared it with various Monte Carlo modelling, and it comes up very well indeed. So now I'm going to stop sharing, and I'll pass over to my colleague Gwen to continue from this part.
So Ralph has given us a bit of an overview over what Varskin may or may not actually do. I'll be covering where do I get Varskin, I haven't got it yet, and also then go through the interface and take you through the various geometries and things you can use, and then that gives you an idea how you might be able to use it. So Varskin is available from the RAMP website, which is basically sponsored by the US Nuclear Regulation Commission. And when you go there to actually get the code, I've got the link here, or you can email us afterwards for a link. You will need to sign up, so register or apply for a membership basically. And then you will need to specify which of the codes you want. So they have various other codes on the website available. Most are for nuclear use, but Varskin is the main one for non-nuclear users, I would imagine. Then once you apply, you will have to sign an agreement. So it's kind of basically a user contract, and kind of you get named licenses. And then you can go, once you have all done that and they have agreed to it, you can then go and download your code. And that's on the codes page, and download, and then you would download. This is the Varskin code for the actual application. Also very important, this vload instructions for installation. My IT ignored that, so it didn't work in the beginning because it is specific on where you need to store the data. And then if you're really interested and have used some of the older versions of Varskin, there's some release notes where you can find a lot of information in depth about Varskin and the changes to the older versions. So Varskin or the RAMP website actually does offer some training modules you can do. They are for the older modules, but some of the very basic things are not that changed that much, but the interface does look quite different to them, but could be useful if you want to know a bit more about geometries and things like that. So now you have Varskin installed. When you first start it up, you get this window, and as Ralph mentioned, we will be talking about SkinDose module today. So when you open that up, you get this window here. And I just wanted to quickly mention these options up here. I think Ralph uses the file, so you can export the file and then upload it again, but there are some issues that Ralph will talk a tiny bit about. And most importantly, to me, is the help button, where you get access to the Varskin help manual. And if you only read one part of that manual, because it's quite lengthy, go straight to Appendix A, where they have all the examples and solutions for using Varskin, where it talks you through a different model and how they progress that model, like spill on the hand, what they kind of input parameters they use, and if they then think, oh, there's a glove, and so on. Some of the stuff I will be discussing today as well. It also has some kind of default values if you don't know what kind of gloves or thickness values you might need for your covers. You can find them on page 14. It obviously talks a lot about the geometry, which can also be useful, and so on. It's definitely worth having a look at that. In SkinDose itself, what we're often interested as a starting point is basically our source geometry. And I was going to talk a bit about, because it's really important that you understand what the different geometries kind of look like. So the most conservative and recommended starting point is to basically do a point source. So that basically models a very small disk in essence and looks at the dose rates from that. And then we have some other geometries that I'll talk through. So next up, we got a disk geometry that's basically a round disk that is infinitely thin. So this is basically the one you want to use if you have a spill on the skin or somewhere else. And you only need to know the area for this one. And Varskin does actually say, as long as you know the area size, it does not make much difference what shape your actual spill is. It should still give a good approximation of the doses you might be getting from that spill. And then we get to, these are all the volumetric kind of modeling things you can do, or shapes you can use. And for these, you typically need to know the density, which Varskin typically defaults to 1 gram per cubic centimeter, I think, and that is basically water, which typically, if we're working with liquids, that will be a good approximation for our modeling. So first up, we get a cylinder. So when we are modeling the cylinder, the difference to the thin sphere is that we have some absorption, self-absorption, particularly of obviously the beta and the alpha. Probably doesn't make much difference for the gamma, but within the column of that disk, and the actual exposure dose that we are kind of modeling is basically from that bit at the bottom here that is in contact. So when you're inputting that, you need the diameter, the height, and the density. The same goes for the slab, pretty much the same thing as with a cylinder, but just a different shape. So you need the width, the height, and the length, and then it will model the dose that you might get from holding it. The sphere is slightly different. Varskin cautions you in using it because it says, oh, very few things are truly spherical. However, what it does do different is that it only has a very small contact point. So when you're modeling something, then it will go through air here rather than be self-absorbed maybe in the column like it is here. So that might be the difference. And it does say also if your shapes don't maybe match quite some of these, you might kind of do 2 modeling runs with like between cylinder and slab or sphere and cylinder to kind of get some bounding values if you are just doing a risk assessment that is to kind of estimate dose rates you might be getting or doses you might be getting from the work you're going to be doing. If you obviously have a specific shape, then you would choose maybe the closest to that. The syringe is actually, in essence, another cylinder, but this time we're looking at dose estimates from kind of that, from the length of the column rather than the kind of area at the bottom. And that would be for syringes, basically we're using the inside diameter and length of the activity inside the barrel of the syringe. And I'm gonna switch now to do a live demonstration. I hope this works. And I will share a Varskin model that I have kind of a little bit pre-prepared. So this is I've been talking about this window. We've got our source geometry here. I've put in P32 and S35, some very commonly used nuclides. So the other thing, really important input parameters that we will need to look at are these exposure inputs. And currently, the dose depth, basically the 7 milligram per centimeter squared. So that's basically a shallow dose, but you can obviously put in other dose. So you could put in a deep dose, so like 1,000 milligrams. Your exposure time, you can set that. I don't know. I just like to set it to an hour, just because we often talk about millisieverts per hour as a dose rate, but you can set any kind of work length or whatever that you might have. Really important, averaging area. In the UK, you would always set it to 1 centimeter squared rather than 10 centimeters squared. That is the 10 centimeters squared obviously comes from the US regulatory regime, whereas in the UK, we're averaging over a centimeter squared of skin, typically when we're looking at dose. So you've reset that. You can then go, also I'll explain how to load the nucleides, but once you've loaded them, you can actually obviously put in kind of whatever activity you will be working with. So I'm just going to put in 10 megabecquerels for both, just for demonstration purposes. So you can see that you can set that to something else. You can also set the dose equivalent units, but I'll leave that at millisieverts, and there it's already done. Oh no, update, and it does my calculation basically. Now I'm assuming, maybe I don't actually want to do a point source, I might do a disk, and then you might have to look at your diameter that you're modeling. So I don't know, for a spill, let's say we say 2 centimeters, and then we calculate and we get a dose for that on the skin. You obviously then need to look at maybe at your exposure time, how long that was there or might be there. For the cylinder, I really like to use it because I think the cylinder is the closest shape you might get to modeling a stock kind of bottle, I guess, or stock vial. So then typically they're not that big, so maybe 10 millimeters by, I'll set that to millimeters, so then I'd go maybe 15. And then I can calculate that again. But so then right on top of the stock, I can then assume that is the dose I might be getting. But obviously I might not be handling it like right with my hand above it, but I might have a bit of an air gap. So then you could set something here, go, okay, let's say 2 centimeters above thing, and you get kind of, and then you can convert that maybe into a dose rate. So since I've set it to an hour, I could say, oh, that might be the dose rate I might be getting during that period of time. And then just quickly to the syringe, just because again here we have the length and then the volume, and the length here, as you can see, is that of the kind of active liquid that you have, not of the whole syringe length. I just kind of wanted to mention that. And then again, you might have to know what kind of syringe your researchers are using to put in kind of some input parameters. I will talk about covers next, but for that I will be switching back. So bear with me one moment. It always takes a moment, but basically when I'm talking about covers, and I will show some slides in a moment when it starts moving forwards again, is the thing with covers is typically you at least want to include a nitrile glove, which does make a big difference, particularly with the beta emitters, obviously. I'm hoping it's still not. Okay. It's a bit slow to come back again. I can't tell if people can now see that the interface. So we should be back on the covers now. So when you want to add the covers, you then click on this button and you get this kind of input window. And in here, for example, I have entered on the screenshot the density that Varskin suggests for a kind of standard nitrile glove. So I have a 0.9 gram per cubic centimeter density and a thickness of 0.05. And then I would click apply, and then it would use that as a cover. This is where I was gonna, I'm switching back to a live demonstration, because I wanted to show that. So well, I think it's a bit slow, but that gives me time to enter the cover. So what you will see is the cover appearing in the little window diagram. So and now you can see in this little window here, it will show me that I'm now currently using one cover, and I'm also assuming an air gap. I might remove the air gap for now. But when you then recalculate it, you should see that, particularly as I said with the beta emitters, it should reduce the dose. The other thing I would enter if I was working with a syringe is basically the wall of the syringe. So typically like some plastic wall of a kind of particular thickness for whatever syringe you're working. And then in the case of S35, it might fully shield me from the exposure. And I will switch back to my slides. So see, that was the interface with the kind of covers. I hope you're now seeing the nuclide list. So obviously I had inputted S35 and P32, but obviously it has a big catalog of nuclides you can input. So you double click on this, it brings up another window with the nuclide list. And that should look like this. I hope this is visible. So you get another window and you see a long list of nuclides that you can use. You see the effective Z that I'll mention in a minute, and then you can select the database from which it will take your nuclide. So you have the option between ICRP38 and ICRP107. And then the other option you have, if you have a decay chain and you want to include that in your dose estimate, then you would use the D option for that incident. And I'll show you what that looks like when you select one of those, because you get some more options. But the other thing with the effective Z is, in essence, Varskin assumes that all you're doing is liquid radionuclides. So it assumes the effective Z of water. If you are wanting to do doses from a solid source, and Ralph will give us an example of that in a moment, then you would have to select a different Z that is relevant to the material that your kind of solid source is made of, and that can make a difference to the calculations, obviously, particularly if you have a volumetric source. Anyway, you then go and select your kind of nuclide, and then as I mentioned, if you have one with daughter nuclides, you should get another window where you put in some decay information. So in the case of a simple decay chain like strontium-90, it will only ask you to put in the time since purity. If that is not known to you, you can just use secular equilibrium. And in essence, that is what Varskin 1.1 does. It doesn't actually ask you, it just assumes secular equilibrium, and you don't get the option of putting a different time frame in. If you have a nuclide that has a gaseous daughter, like uranium-238, then you also need to put in a gas emanation factor. I hope Ralph mentioned about that a bit more, because he is using U238 as an example. Otherwise, you might have to troll the literature to look at those emanation factors. So then you've added that into your window. In my next example, you can see I've added F18P32. There's a couple of other things that you can find about your nuclide, or other input values you can use. So you can click this here to put in if you know the source strength of a volumetric source. So basically, if you know the activity in, I don't know, say becquerel per cubic centimeters or something like that. Then you can put that in here instead, and it will change over that window. The other thing that is really useful, I guess, is for very short-lived isotopes, like F18. When you click on these on the dose detail here, it will give you the dose without decay correction, and you can see that in this example here, this is a different dose to the one I'm getting here, because in an hour's time, there is some decay correction. It's already decaying away because it's only got 110 minutes half-life. So without the decay correction, the dose is different. The other thing that is also really useful here is you could get the initial dose rate, which might be useful if you want the dose rate rather than the dose. And then we also can get, there's a lot of information crammed into Varskin. So you can also get nuclide info when you click on the button here. And that gives, like here, I've selected something a bit more simple, P32, half-life. X90 distance is a medical value. It basically tells you what distance 90% of your particles, I think, will go in water, if I got it correct. But medical people, feel free to correct me in the chat. Anyway, because it's not something I use really normally. You get the average value, energy of your nuclide, but you can also look at the spectrum, as Ralph mentioned earlier. This can be important. And then if you have a more complicated nuclide, you'll get here you might get loads of different emissions, the kind of yield you get from them, and so on. And just one last word about the special options. Typically, for your normal day-to-day stuff, you probably wouldn't use them, and Varskin doesn't actually recommend using them unless you're like some sort of modeling whiz. And then you might be saying, okay, I want a different averaging area here. I think there are some examples. It mentions an ICRP where you look at skin damage and things where you might use a different volume averaging area. And then the other thing it does, obviously, you typically looks at the skin outside, the source outside on the boundary to the skin, so it's in air. If your source for some reason is not in air, then you might do some wonderful things by disabling those kind of backscatter corrections it normally assumes. But as I say, I don't really use it. It's a bit specialist. And I think with that, I will hand back to Ralph.
Just listening to Gwen, it sounds awfully complicated, but we both found actually that Varskin is quite intuitive. Once you play around with it, it's fairly straightforward. Things are where you expect them to be, and so certainly when I first came across it, I just played around with it for a while. It's got the feel of how it works. I'll give you some examples here, and this is not about skin contamination. It shows you the versatility of Varskin. One of the things I used it for was to determine whether I needed a tool to handle a vial of eluate from an elution source. Because using a tool, you're transporting a small amount of liquid increases the risk of spill very, very greatly. Far better if you can handle it by hand. And using Varskin, I was easily able to model what the dose to the finger was in transferring a vial of solution of barium 137M from one place to another over a few moments. Now I'm going to show you one now that's a little more complicated. And again, it shows you how Varskin can be used. So I'm going to look at, if someone were handling a disc of depleted uranium, what would be the dose and dose rate to the hand? I've got an example up here. So there's the disc, and I've given you some physical data about it, the dimensions, the age, the density, which you can look up. The effective atomic number is just the order for an element, it's just its atomic number, it's 92. The person's wearing a glove, and we need to know what the radionuclides are. Now, the rookie mistake you could make is put in U238. When uranium ore is chemically refined, because it's in secular equilibrium, it's got equal activities of uranium-238 and uranium-234, both in the decay chain. However, when it goes through the process of being refined for nuclear fuel, it becomes what's sold to us is depleted. And so the levels of uranium-234 are much less, as is the quantities of uranium-235. If you just put in uranium and the decay chain, it will assume there's only uranium-238. It will not know there's uranium-235. It will not know, Varskin will not know there's uranium-234. So you need to put in all three radionuclides as the head of chain. So to do that, you first of all model it as a cylinder, as Gwen has shown you this morning, and the dimensions and the thickness and the density, because there can be a large amount of self-absorption of the beta in the disk of uranium. That's fairly straightforward. And then the next window, you put in the exposure time, and I'm going to put in an hour, and that will give me the dose rate. And from that, I can figure out the dose depending on how long the person's holding it. And you must change the averaging area to 1 square centimetre. Gwen's gone through that with you. And again, the covers that Gwen's gone through with you. Up comes that little window, and I put in there the typical density. And I've got a fairly thick glove there, a millimetre, which I put on the 0.1 millimetre, which I put on the screen there. You don't enter anything in the third column, a density thickness. It works it out for you. Just click the apply button, and then you've applied the covers. The next bit is to load the radionuclides. So you click on that button on the left there. So I'll just place a pen. So you click on that button there, and then you get a separate screen coming up. Just for convenience, the order is important. If you get the order wrong, it doesn't mess it up. It just means you've got to go back and do it again. So you first of all click on the database you want to use. So I've got 3 radionuclides head of chain. The first I'm going to deal with is uranium-238. I want to deal with the whole decay chain of uranium-238. So I'm going to click on ICRP 107D as my database. Then I put in the effective Z, which in this case is 92. And then I go to uranium. Now, rather than scrolling through everything, if you just hit the U button on your keyboard, it takes you straight to U's in the database. From there, I can cursor down, scroll down, and go to uranium-238. Then click on Add. And that little wheel goes round and round. It can take quite some time, so be patient. And then this screen comes up. And Gwen's gone through that. It's the time since purity. Well, I'm assuming it's 10 years old. So I put in my time, and you get this, the outgassing. This is tricky. For uranium that's been chemically extracted, the decay chain pretty much stops after uranium-234. So there's not going to be any significant radon in the decay chain. So I'm going to put 0 for my outgassing factor, because this is only used when you've got radon in the decay chain, and you can lose some of it as it escapes. If you've got thorium, then it's a little bit higher, because the decay chain does go down to radon 220 over time. My rule of thumb is if it's the radium decay chain, the radium 226, and you've got something like radium paint, then I would use a factor of 0.2, 20% outgassing. If it's something that's in bad condition, you could go to 0.3, 30%. If it's a powder, again, I would go to 0.3. But if you're not sure, leave it at 0, and then you'll get a pessimistic result. And then you can say, well, it can't be any worse than this, the dose. And once you've selected that, I'll just flag up the problems with effective Z. So, okay, it's straightforward for water, for the materials that are listed in the document that comes with Varskin, for stainless steel and other things they give you, it's fine. But what about uranium oxide or something like that, where you don't know the effective Z? There is a formula you can use. There's no notes in it in the Varskin documentation, but there is actually a very good page on Wikipedia that goes through this formula which they use in Varskin to calculate the effective Z. It is somewhat iffy, and there's various literature put doubt on on how accurate that is. There is a better method. It's some software. It's free, but again, it's not available on the website. You have to apply to the authors who wrote it. So I asked Professor Rick Fanish for this, and you put the details in, and it gives you the effective Z. The trouble is, it's too good in some respects because look, can you see the effective Z is energy dependent. So what you have to do is look at the average energies that are coming from the radionuclide and choose the effective Z. So it's your call, your decision on what to use. Having done that, I need to put my other radionuclides in. So I've got uranium 235 and 234. So the same procedure, you tap U and it goes down to the uranium, and I pick the relevant radionuclide. When I've done that, I finally click on close the window on the top here. And then this wheel will whir around and you come back to your main screen where I'm going to enter the activities that are in the head of chain. I'll go back one slide. I'll flag something that's a quirk in Varskin 1.2, and we have flagged this with the authors. It takes quite a time to transfer the data from the database into your working database here. So what you can do is press this left arrow here and transfer it into your local database. It stores them in there so you can retrieve them much more rapidly. There's a bug, because if you put anything from the D databases, when you put them in here, you can't get them back again. The workaround is just reload them, but it's just a pain. So just be aware of that. We hope in a fairly an update to come soon, that'll be corrected. So back to this main screen, you pop in the activities and then you click on calculate, and it whirs around and you get the doses over an hour. So that's the dose rate for the depleted uranium, and it's dominated, unsurprisingly, by uranium 238 because it's dominated by the protactinium 234M in the decay chain. So in this case, these two don't make a great deal of difference. At least you can justify it. So there's an example of using something that's not strictly contamination, but you'll want to work out the dose and dose rate from holding something, perhaps to justify a procedure. Works, ones we've found so far, we have reported these, and some of these are long-standing and a bit irritating, but there are workarounds. There's a feature in Varskin that once you've done the modelling, you can save it, so then you can retrieve it later on. That's really helpful, but when you retrieve it, you find that the covers data doesn't get loaded. Now, you can retrieve that because when you save modelling, it saves an XML file. So you can just open up the XML file in a text app, and you can scroll through and find the covers data. It's just annoying that it's not loaded in. So if you're not careful, you'll load your example back in at a later date, run it again and get a different answer. You won't know why. Well, it's because the covers data has not been loaded. Second one I've mentioned already, that you can't retrieve your ICRP 38D or 107Ds from your local database into your working database. You have to reload it in from the main databases. Another quirk we found that if you retrieve a saved modeling, but you haven't got the radionuclides in your local database, it won't work, and you get erroneous results. So make sure that when you're loading the previous modeling that you've saved into Varskin to run again, that you do have the relevant radionuclides in your local database. And there are two things we can't replicate, but we have flagged the authors. Sometimes when you look in for dose detail, it comes up with NAN, not a number. We don't know why it does it. Really, we don't know why it does it, but if you rerun the calculation, it often fixes the problem. And lastly, Gwen's come across this one, and we can't replicate it. Occasionally, if you're using the decay chain databases, when you come to put in the activities, it won't let you. It locks on 1 becquerel, and you can't change it. And the fix is just restart it and do it again. That seems to go away. So, as I said, we have flagged this. In the research to this, come across this, you may be aware of it. I wasn't. I'll just flag it. It's in ICRP 147, which is on our units, operational units for doses. There's a move to not use equivalent dose as a protection quantity for extremity doses for the hand, rather to go to absorb dose. But to keep equivalent dose as a stepping stone to calculate effective dose. Now, obviously, this is fairly new, but ICRP is authoritative, so I suspect in time we may well find that things change, and we'll see the dropping of equivalent dose in terms of setting dose limits in legal terms and moving to absorb dose. So watch this space. If anyone knows more about it, we'll be delighted to hear. And thank you. That brings us to the end of using Varskin.